Hi everyone, my name is Liran Funaro and I want to talk to you about cloud elasticity. Specifically, why do we need memory elasticity in the cloud, how to create memory elastic applications, and how to benchmark them. Any business aims to maximize its profits, and cloud providers are no different. Improving the resource utilization is one way for cloud providers to improve their profits. In previous paper we showed that offering resource elasticity instead of rigid allocations achieves exactly this goal. For example, cloud providers offer a dynamic bundle called burstable performance. In this bundle they offer basic level of CPU performance but allow clients to burst to a higher level when required by using resources that are unused by other clients at the moment. When cloud providers offer burstable performance, in addition to rigid allocation, they can allocate significantly more clients to the same physical server. But once we allocate more clients to the same server, the memory becomes the main bottleneck. So naturally, we would like to extend the burstable performance idea to support burstable memory. We want to allow clients to momentarily request memory in addition to their initial memory allocation when it is momentarily unused by other clients. And for that, we need two things. First, we need applications that can burst, but we have plenty of these. Many applications consume additional memory at momentarily peak loads and release it when the loads return to normal. The second thing we need, and this is the challenging one, are applications that can function well when their memory requirements are not satisfied. Because that's something that can happen if many clients observe peak load at the same time. So what does function well means? It means that they should be memory elastic. Their performance should be proportional to the available memory rather than just drop to an unacceptable levels when their memory requirements are not met. But unfortunately, the latter is true in most cases. Applications' memory usage is mostly dictated by the current application workload and not by the memory availability. When there isn't enough memory for the application, the OS swapping will kick in, and that does not satisfy the function well rule. Even a minor memory loss will degrade the performance significantly. So why is that? Why do developers make so much effort making performance scale so nicely with the CPU, but neglect doing so for the memory? The mechanisms for CPU elasticity were already there for entirely different reasons, and we just exploited them. But memory elasticity requires effort by developers which they lack incentives to do so. A cloud offering of burstable memory could have been sufficient incentive, but this does not exist yet, and it will not exist until a proof that such memory elastic application actually exists. In this work, we aim to break the circular dependency to ignite future work on this subject. First, I will list several methods in which existing applications can become memory elastic with relatively low effort. Then I will present a method that developers can use to measure how memory elastic is an application. Finally, I will demonstrate this measurement on an application that was modified to be elastic. Let's start by reviewing some of the methods that can be used to convert an application to be memory elastic. And the way we are going to achieve that is to utilize mechanisms that were designed to allow a trade-off between memory and other resources. First, we have applications that use memory as cache. Memcached, for example. They often trade off network and CPU with memory. Such applications can seamlessly improve their performance when more memory is available by enlarging the cache. When the memory is scarce, they can use their built-in eviction policy to evict some of the data. Second, we have applications that use the memory buffers to process data from one source and deliver the result somewhere else. For example, fetching many vectors from a remote agent, multiplying them, then storing the result to disk. Such applications' performance is often affected by the size and number of these buffers, so it can adjust the buffer settings according to the available memory. Third, we have applications with automatic memory management. Java, for example. When the memory is scarce, the applications will have less headroom for allocations, resulting in more GC cycles. So when allocated more memory, the runtime can increase the heap size and improve the application performance. Last, we have short-lived job schedulers. Web service, for example, requires some memory to handle each session. Such applications can handle more concurrent sessions when more memory is available, so their concurrency can be tuned according to the available memory. Note that the example applications that I mentioned before are in fact memory aware, but not memory elastic. This means that they can adjust their memory consumption according to the available memory that was observed during startup, but not during runtime. We can restart these applications when the memory availability changes, but it may result in poor performance and will not fit users that require continuous availability. But with not too much effort, we can modify applications that use one of these trade-offs to be elastic. For example, we adapted memcached to support memory elasticity by forcing it to change its memory footprint upon receiving a command via socket. But what did we gain by this effort? Is this memory elastic memcached better than the off-shelf one in a dynamic scenario? How would we even measure this? We could, for example, randomly pick a series of memory availability values and measure memcached throughput when applying these memory changes during runtime. But that's just a single scenario. What will happen if we change the memory more frequently? What if we will increase the size of the changes? A single scenario won't give us the full picture. This is because we try to infer memory elasticity from observation of metrics that only hint about elasticity, but do not measure it directly. So, our goal is to quantify applications' behavior in dynamic memory scenarios using metrics that directly relate to memory elasticity and are comparable between different applications. First, we look at static metrics, those that measure static scenarios. In the graph we see the memory to performance function called pmem. It shows what will be the performance of the application given different memory limitations. It also shows what is the minimal memory the application can function with, and what is the maximal memory that the application can still use to improve its performance. Let's look at memcached for example. In our memcached workload, its elasticity domain was from 1 to 3.5 GB. This means it has an elasticity range of 2.5 GB. Note that these metrics are true for both off-the-shelf memcached and our elastic version, which indicates that our static metrics are not enough. Dynamic metrics should measure the effect of the transition between memory allocations. An application might require some time to utilize the added memory. We call this time period tmem. For example, it takes time to fill the cache, and it takes even longer to notice an improved hit rate due to the reuse of cached items. This is depicted by the leftmost tmem in the graph. Upon memory reduction, an application might need to prepare for eviction a few seconds ahead of the change to avoid memory swapping. This is depicted by the rightmost tmem in the graph. Let's focus for a second on the leftmost tmem. In the same time period, the performance could climb up at many different rates. Here is an example of two different applications with the same tmem, but completely different climb rate. Our dynamic metrics needs to be able to quantify the difference between these two applications. For that, we simply look at the area above this application's performance graph during this time period. This is the difference between the performance that the application should have shown to the one it shows. Notice the new graph to the right. It represents the same two applications, but we manipulated their performance to remain the same for some time and then immediately climb to the expected performance. The connection between these two graphs is that the area above the graph of each application is identical in both of them. Looking at the right graph, we consider the time period until the application performance climb to the expected performance as the effective tmem, or emem in short. And now we can clearly see the difference between the emem of these two applications. Going back to our memcached example, we can see here the measured emem of the elastic memcached for each memory transition. The bottom right part of this heat map is for memory reduction, and the upper left part is for memory addition. This shows that our elastic memcached can release memory effectively when needed, and can fill up its caches fast enough to be useful. We also measured the off-the-shelf memcached by restarting it on each memory change. Since shorter emem values are considered better, we can clearly see that our modification significantly improves the memory elasticity of Memcached. To sum up, we showed a few major building blocks of many applications that can be made memory elastic: cache, intermediate buffers, garbage collection, and schedulers. We defined metrics that are comparable across applications, elasticity range and and we define characteristics that can be used by clients to configure their virtual machine and their application in a memory elastic cloud environment, PMEM and TMEM. In the paper we show how we measure the static and dynamic metrics and how we validated that these metrics are meaningful and useful. Thank you very much for listening, and I'll be happy to take your questions.